Welcome to EDU World Space.
A fairly basic equation in astronomy relates the flux experienced from a star that we observe on Earth to what is known as its apparent magnitude. It is a relative scale, so m in this case is apparent magnitude. It is a relative scale that's pretty much arbitrarily decided by how our eyes work. Our eyes determine intensity of light on a logarithmic scale. And it was just noted that two stars that differ in magnitude by 5 have a relative brightness, of course, of 5 magnitudes, but the flux ratio is about 100. So the scale was standardized, the apparent magnitude scale related to flux. And here in this formula, you could be relating the flux of a single star at two different distances, or you could be comparing the flux of two different stars in terms of their apparent magnitudes. So another relationship that you can develop from this is to calibrate it according to a absolute magnitude. And this is a little bit clunky, but absolute magnitude is defined to be the magnitude the star appears if it were at a distance of 10 parsecs. So there we are going to call F1 the flux of a star at any distance compared to its flux at 10 parsecs. So there's the definition of absolute magnitude. And this would be 100 times the absolute magnitude of the star minus its apparent magnitude divided by 5. By the way, this set inside of here is called the distance modulus. If you had some way of knowing the magnitude of the star at 10 parsecs, and then finding its apparent magnitude, you could use that distance modulus to actually calculate distance. So I will point out that there is an inverse square law built into this relationship. So that's interesting. Anyway, how can we use this relationship? Well, there's different ways, but we could compare an unknown star to a very well-known star like our sun. Because we know our apparent magnitude of our sun, we know its actual flux. We can calculate how bright it would appear at 10 parsecs, and thus its apparent magnitude. So we could use that formula to do some things to compare an unknown star to our sun. So in the following, I'll use the symbol asterisk to represent an unknown star, and the canonical symbol for our sun is a circle with a dot representing our solar system. But if we use the first equation, we can write down F star unknown to our sun in terms of the flux is, of course, 100 times the difference in their apparent magnitudes. And we can use, so this is really kind of using equation 1. we could use equation 2 and calibrate our sun based on a distance of 10 parsecs. And then we put in the absolute magnitude of our sun minus its apparent magnitude. And then we can use this second equation to substitute in to our first equation. Okay, so the flux of our sun is equal to its flux at 10 parsecs times 100 times the difference between its absolute and apparent magnitudes in the exponent divided by 5. Okay, and then we can kind of manipulate this into formula number 1. Just substitute it in. We'll do a little bit of cross multiplying. And what we'll have is 100 times 1 exponent times 100 times the first exponent in terms of the star. And you remember, if the base to which the exponents are raised is the same, you just simply add the exponents. And we'll see what happens there. Some stuff cancels. And so we're left with a fairly simple relationship that we can take a logarithm to base 10. So remember, that's how you get rid of exponents, is to take a logarithm. And you can take a logarithm to any base, but astronomers like base 10. Okay, so take logarithm of base 10 on both sides. And remember that the logarithm removes an exponent out as a multiplier. So down comes our exponent with the two magnitudes, the absolute magnitude of the sun, the apparent magnitude of the star, and then we have log base 10. And did I forget 5? Yes, I did. Okay. Yeah, let's get the 5 back in there. It just hangs out. Log 10 of 100. And now you can see why we like base 10. Log 10 of 100 is just 2. 100 is 10 squared. And the log just pulls out the exponent of the base. Okay, so kind of manipulating this further, log base 10, the flux of the star divided by the flux of our sun at 10 parsecs. Let's cross multiply by 5 over 2. And then that simplifies to just the difference in the two magnitudes. And of course, we can rearrange this in any way that we see fit. it's probably best to think about what is our unknown. Let's assume that our unknown is the apparent magnitude of the star. So we move it to the other side of the equation, and we've got it's the absolute magnitude of our sun minus 2.5 times the log base 10 of the ratio of the two fluxes. And this would be helpful if we could figure out the flux of the unknown star. But it does relate the apparent magnitude of the unknown star to some known quantities.